Good morning. It's July 9th and this is your daily brief in science. Here's everything you need to know. A new effort to bring back an extinct bird is underway, involving a collaboration between biotech company Colossal Biosciences, filmmaker Peter Jackson, and the Ngai Tahu Research Center. The project focuses on the MOA, a flightless bird native to New Zealand that went extinct roughly 600 years ago. Researchers are working on extracting DNA from well-preserved moa bones, including some from Jackson's personal collection. They are comparing this DNA with genomes of living birds like emus and tinamous to identify what makes MOA unique. Experts question whether reintroducing moa into the wild is feasible due to ecological and ethical challenges. The project is expected to take up to 10 years and involves genomic biobanking and funding Maori-led expeditions. Colossal CEO Ben Lamb emphasizes the cultural significance and plans to house the revived MOA in ecological preserves rather than releasing them immediately. Jackson, who has sampled moa bones for DNA, sees the effort as a redemption story that could inspire conservation and scientific interest. The team aims to complete the first genomes by summer 2026. The project involves significant costs, estimated in the 8 figures, and aims to advance genetic research with potential biotech and environmental benefits. Jackson's involvement also connects to his work on the upcoming film The Hunt for Gollum, scheduled for release in December 2027. The initial focus is on reviving the South Island giant moa, with hopes of eventually bringing back all 9 moa species. This model of indigenous-led conservation could set a global precedent for de-extinction efforts, blending genetic science with cultural and ecological responsibility. A recent Phase 2 clinical trial has shown promising results for bria-imt, combined with checkpoint inhibitors in heavily pretreated metastatic breast cancer patients. The study involved 25 patients, with a 1-year survival rate of 52%, and some patients surviving over 30 months. Experts highlight the significance of these survival data, especially given the difficulty of treating this patient population, and suggest that bria-imt could improve outcomes for late-stage metastatic breast cancer. These results surpass current standard care expectations, indicating potential for meaningful clinical impact. However, BriaCell, the company behind the therapy, is operating with negative cash flow, having spent $3.36 million in the past year, making upcoming trial outcomes critical for its future. The trial's treatment schedule includes 3-week cycles of therapies such as cyclophosphamide, SV-BR-1-GM, checkpoint inhibitors, and interferon, with imaging assessments every 6 to 8 weeks. BriaCell's ongoing Phase 3 trial has expanded to 58 sites across 15 states, with patient enrollment expected to conclude by early 2026, and top-line results anticipated in the first half of that year. The encouraging data from these studies support confidence in bria-imt's potential to improve outcomes for patients with advanced disease. A Phase 3 pivotal trial, NCT 060722612, is currently underway to provide more definitive efficacy data, comparing bria-imt plus retifanlimab against physicians' choice treatments, enrolling up to 404 participants. Patients in the study had previously failed multiple therapies, including checkpoint inhibitors and antibody-drug conjugates, with a median of 6 prior treatments, yet no treatment-related discontinuations were reported. The therapy has demonstrated a favorable safety profile, with no discontinuations due to treatment side effects. Follow-up data indicate a survival advantage over standard treatments, with some patients surviving beyond 30 months and long-term responders reaching up to 38.3 months. These survival outcomes significantly outperform benchmarks from similar studies, where 1-year survival rates typically range from 23 to 40%. Recent research has revealed a new feature of aggressive cancer cells involving organized waves of glycolytic enzymes on their membranes. These waves are observed in cancers such as breast, pancreatic, lung, colon, and liver, and are absent in normal cells. The enzyme-driven waves are linked to increased ATP production, especially in more aggressive cancer types, suggesting a connection between wave activity and tumor severity. These waves are generated by enzymes involved in glycolysis, the process that breaks down glucose for energy, and are more common in highly aggressive cells. The discovery indicates that energy waves help coordinate cellular behavior with metabolic needs, allowing cancer cells to rapidly adapt their energy infrastructure. This mechanism provides a mechanical explanation for the Warburg effect, which describes cancer cells' preference for glycolysis even in oxygen-rich conditions. The presence of these waves across various cancers points to a common feature of aggressive tumors, making them a potential target for therapies. Wave activity correlates with the level of glycolysis reliance in different cancer cell lines, positioning it as a marker for cancer progression. Scientists at Johns Hopkins Medicine have shown that rhythmic enzyme activity creates these energy waves, which may fuel tumor growth and metastasis. Disrupting the waves with molecules like latrunculin A has resulted in a 25% decrease in ATP levels, highlighting the cell's dependence on these energy structures. Ongoing research aims to understand the mechanisms behind wave formation and regulation to develop targeted treatments. Researchers have developed microchannel systems that replicate narrow tissue spaces within the body, enabling the study of how physical confinement affects stem cell behavior. Experiments with mesenchymal stem cells, or MSCs, show that squeezing these cells through 3-micrometer-wide channels causes lasting changes in their structure and gene activity. Notably, this process increases the expression of RUNX2, a gene associated with bone formation, indicating a shift toward osteogenic differentiation. This phenomenon suggests that physical confinement can create a mechanical memory in stem cells, with effects persisting even after they exit the confined environment. The ability to influence stem cell fate through mechanical forces alone introduces a chemical-free approach to tissue engineering. Led by Assistant Professor Andrew Halla at the National University of Singapore, the research emphasizes that physical forces during microchannel confinement induce genetic and morphological changes in MSCs. These findings open possibilities for prompting stem cells to become bone cells without chemical stimuli, potentially simplifying regenerative therapies. Scientists are also investigating whether similar mechanical preconditioning could apply to more potent stem cell types like induced pluripotent stem cells, or iPSCs, and whether early embryonic development could be influenced by mechanical forces. The broader implications suggest that mechanical forces during early development might impact cell fate decisions, with potential effects on tumor migration and tissue growth. Published in Advanced Science, this study highlights that physical confinement not only alters cell shape, but also promotes genetic changes favoring bone formation, marking a significant advancement in mechanical preconditioning for regenerative medicine. This approach challenges traditional methods reliant on chemicals, offering a more scalable and potentially safer alternative for stem cell differentiation. Researchers aim to optimize the mechanical properties of biomaterials to guide stem cell behavior more reliably, enhancing applications like bone repair and tissue regeneration. Dr. Qian, an assistant professor at the University of Pennsylvania, was inspired to study neuroscience after watching the anime series Evangelion. This interest led him to pursue biomedical engineering and develop innovative methods for creating human brain organoids. His brain organoid technology has significantly impacted neuroscience research, with over 2,000 citations, and has advanced understanding of neurodevelopmental disorders. His work has potential therapeutic implications, aiming to improve early diagnosis and treatment for conditions affecting millions of children worldwide. During the 2015 to 2016 Zika virus outbreak, Dr. Qian's research provided key evidence linking the virus to microcephaly, influencing CDC guidelines to protect pregnant women. His recent study created a developmental atlas of the human cerebral cortex by analyzing over 18 million brain cells. Using MERFISH technology, his research offers one of the most comprehensive analyses of human brain development to date. As he establishes his lab at the University of Pennsylvania, he plans to integrate brain organoid models with spatial omics and human genetics to investigate disorders like autism and cortical malformations. Recognized on the Forbes 30 Under 30 list, Dr. Qian emphasizes collaboration and open science. He also actively communicates science through platforms like Bilibili to make neuroscience accessible and inspire future researchers. His work is featured in Genomic Press's Innovators and Ideas series, highlighting his contributions to advancing neuroscience. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.